Afternoon, everybody. Thank you. For anybody that wants to go and get coffee, I'm not John Allspar. I'm sorry. So he's rushed off to America because it's going to snow badly, and that seems to play into his resilience engineering talk to me somehow. That's kind of interesting. This isn't really a keynote style talk. This is kind of a different thing. John had the challenge of trying to squeeze a 60-minute talk into a 40-minute slot. I have the luxury of trying to expand a 40-minute talk into a 60-minute slot. In reality, I've got 82 slides, and I'm still not confident that I'm going to fit it all in, so I'm going to talk quite quickly. So I want to talk. This is a talk about. Okay, so here we're kind of all early adopters. We've been doing a lot of this stuff for a while now. So there's the first flush of excitement and enthusiasm of the first time you press a button and it runs all the tests and it deploys into production. And you go, oh wow, this is magic, and then you live with it for a while. And other sorts of problems crop up over time. And I want to talk a bit about those sorts of problems, because we don't always talk about those. We're often talking about the fresh stuff of just introducing this stuff for the first time. So my talk is really about that. I'm expecting these next few slides, these handful of slides, to be revision for everybody in this room. But I just want to remind us of what we're all talking about. So what do we really want? We want to be able to have an idea. We want to be able to get that idea into the hands of our users, and we want to figure out what our users make of it. Fundamentally, that's what all of continuous delivery is about, and that's what all of software development is about. That's pretty much it. So we want to optimize for that. We want to make that efficient and fast. We want to have feedback loops, and we want to establish feedback loops in multiple places to be able to get fast feedback. And the quicker and the higher quality of the feedback that we can get to the source of the change, the better the work goes, the higher quality of the work, as a general principle. We want to start working in experimental ways. It doesn't matter how intelligent you are if you guess, and that guess can't be backed by experimental evidence, then it's still only a guess. So we want to start moving away from guesses. We want to start measuring things and evaluating things and learning from those. We're going to use cycle time to kind of target and drive forwards to learn and adapt and understand. It's my belief, and some of you might have heard me say things like this, similar things before, but it's my belief that if you employ an empirical kind of experimental approach to solving problems, and you apply that approach to trying to optimize your cycle time to make your feedback cycles shorter and more efficient, you drive out, as a natural consequence, pretty much all of agile theory, all of lean thinking, all of DevOps, all of continuous delivery. All of those things. And so these are good tools to have. These are good ways of moving forward. And that's kind of the starting point. And then we've got the principles of continuous delivery. We want to make our releases reliable and automate everything and keep everything under version control and bring the pain forward and build quality in and all of those sorts of good things. And finally, we've got a deployment pipeline. We've got this mechanism that allows us to evaluate an idea and understand it and give us feedback, and it gives us an organizing principle, a way of thinking about these things and organizing them in a way that we can learn quickly and adapt to what we learn. My kind of starting point for a minimalist deployment pipeline, if I was writing software for my mom's cake shop, I'd probably start with a deployment pipeline that was this simple. But this is kind of my minimal thinking. You're going to have some commit tests that evaluate the software from the point of view of developers. You're going to have some acceptance tests that think about it from the perspective of users. And you're going to automate all of the provisioning and the deployment and all those sorts of things. And we can extend that depending on the nature of the project. We can have more fully formed pipelines. But those principles kind of are kind of fundamental to the establishment of a continuous delivery process, to my mind, the way that I think about it. And this is my map. I'm going to use this as a bit of a map of the process as we go through. So we've done all that. We've thought about that in our projects. We started working on our projects on that way, and we started applying this kind of thinking. And we've been operating it, and we've been getting some good results. So where do we go from there? So one of the first questions that seems to crop up very frequently in the organizations that I talk to these days is, but what's the scope of a deployment pipeline? How much stuff should I evaluate together? What's the boundaries that matter? And My wife says that I'm a serial nerd. She's wrong. I'm a parallel nerd because I can be a nerd on multiple fronts at the same time. And one of my nerdisms is aeroplanes, and so forgive me for the aeroplanes. But so we could think about the scope of a deployment pipeline. Here's a system. What's the scope of stuff that matters here? We could think about, is it that piece or this piece or this piece? Actually, it's not. We want the whole thing. In this context, we want a deployable unit. We want an independently deployable thing, and we want to know that that thing works together as a thing. That's what we're interested in. Maybe we've got a different kind of system. Maybe we've got a system that's composed of multiple independently deployable things, and we can think of each of those having its own deployment pipeline to evaluate that deployable thing in isolation. And that's a good pattern as long as they're independent of one another. As soon as there are dependencies between them, we start making all of this more complicated. So the independence of these things, so we can, in a system like this, we could add a new thing and that could have a separate deployment pipeline. We could take away another, and it doesn't have any impact on the system as a whole. And that's a useful way of thinking. I'm kind of talking fundamentally about the difference between kind of treating things as a monolith and treating things as maybe microservices or whatever. But one of the crucial aspects of that is an independently deployable thing. So the first thing to consider in terms of continuous delivery from my point of view is the scope of a deployment pipeline is an independently deployable unit. I see far too many organizations that try and create a deployment pipeline, and then they build dependencies between all the deployment pipelines for all of their pieces because that thing depends on that thing, and I need to know that those things work together. But if they work together, they belong together, and you want to deploy them together, and you want to test them together. So that's one deployment pipeline, not many. Next, where to test. Where do we want to test in terms of our development strategy? What about branching and all those sorts of things? So we've got our idea, and we want to get our idea into production. And commonly these days, we think about ideas like feature branching. We're going to create these different branches of development. And if we've got a model like that, where does it make sense for us to apply our testing? So we could do some testing here, we could do some here, or we could do some there. That's actually the only place that makes any sense in this picture, because before that, any testing that we do earlier than that isn't taking into account all of the different variants that could occur on these different branches. So that makes sense over there, but the downside with that is that that's a long way from the idea, which means that our feedback is compromised. The rate at which we gain our feedback is now slower. So there's a problem with that. It's that we're deferring the gratification of getting good, high-quality feedback on our ideas by feature branching. Maybe what we could do is that we could test here. And then we're never testing what ends up in production. We're always testing something completely different. So we don't know what's going on here. So this happens all of the time. So that's a problem too. So on the whole, I'm sure that Elizabeth is right. There are times when there may be a pragmatic reason to choose feature branches, but we shouldn't. That shouldn't be our default position. That should be an exception in very exceptional circumstances when we can't come up with something smarter. And the smarter thing, the thing that gives us the most efficient feedback, is to put everything on one branch, on trunk, have an idea, and get that into production as quickly as we can, get high quality feedback, test it there, and then we'll understand what's going on. So, my advice on branching strategies. Don't branch, don't branch, don't branch. I actually added something to the definition of continuous integration a long time ago, and my addition to continuous integration is you're not performing continuous integration unless you're committing at least once a day. So if your branches last for less than once per, less than a day, I have no argument. I might question your sanity on why you bother at that point, but I have no argument against them. If they last for longer than a day, you're not doing continuous integration. So, the rest of the talk is really about the pipeline. The rest of the talk is really about thinking about that and how we live with that as we've got to these more sophisticated ends of our testing. So, the first thing to think about is that we want our pipeline to be our only channel to production. any change to our production system goes through the pipeline. We want to evaluate it for our deployable unit, whatever that thing, our independently deployable unit. We want to evaluate any change. Configuration of our system, change to the operating system, change to the language, change to the libraries, change to the database, change to the schema, change to the source code. Any of those things, shove it through the pipeline, evaluate it and see if it works. All change to productions flow through it. If it breaks, it's going to have a fairly serious impact on our ability to deliver software. So, very rapidly, for organisations that become mature in the adoption of continuous delivery, the pipeline and the infrastructure that surrounds it becomes a strategic resource. This is your only channel for production. Even worse than that, if your pipeline breaks, you've lost visibility. It's like driving in the fog. You don't know what's happening, because if you're making changes in your development process, you don't know where you are. You don't know how you're breaking things. So not only does your ability to release into production fail, you've now got no insight into changes. So really, the safest thing to do is to stop all development. So it's important. So you might start thinking about how to protect it and how to, make sure that it's resilient over time, and think about ideas like service level agreements and so on. The other thing that tends to happen over time is that we get addicted to the feedback that we get, and we want higher quality feedback. We end up in a situation in the mature organisations that practice continuous delivery that I've seen, of becoming really obsessed by testing, and we want to test everything. And so we get thousands, tens of thousands, maybe hundreds of thousands of tests to execute. So things start going slowly. Our software gets bigger and more complicated. And so all of these things become problems. We've got slow commit stage, slow acceptance test stage, failing tests, intermittent tests, and changes to the pipeline that might all impact our ability to get that crack cocaine and fast, valuable feedback that gives us insight into our creative processes. So I want to kind of go through each of those and just explore those in a little bit more detail. So let's start off with the slow commit stage. So here's our map of our deployment pipeline, and this is the bit that I'm talking about now, the commit stage. And this is kind of my mental model for the pseudocode algorithm of the kinds of things that you probably want to do in a commit stage. You want to probably compile your code if your language has a compilation stage. You want to run some unit tests for sure. You probably want some static analysis as well of your code at this point, and you want to build the installers, the deployable units, the jar files, the .NET assemblies, the Docker images, whatever it is, you want to create those things at this point, because from now on, that's what you want to test, the release candidates that were at the output of the commit stage. So let's go through those. In an ideal world, the recommendation that I tend to give my clients is that an ideal cycle time for this stage in the process, the feedback cycle rather, is 5 minutes. What you want is that you want feedback in 5 minutes or thereabouts. And there's a good reason for that. And basically, it's because I'm a developer and I've got very limited attention span. And so if I make a change and it takes more than 5 minutes to give me an answer, I've kind of lost interest. And what I'm going to do is I'm going to think, that's way too long. So what I'm going to do is I'm going to store up and wait until I've got a big enough change to make it worth checking in. So if you have a longer feedback cycle than about 5 minutes, it tends to force your developers into holding back on commits. It increases the batch size. And we've all listened to lots of the excellent speakers today telling us that small batch sizes are really important. And they are, because that's the kind of the oil that greases the wheels of the process and makes it all work efficiently. So we want to try and keep our feedback cycle in our commit stage to under 5 minutes, whatever the size of our system, which means that this is really, really valuable real estate. The commit stage is probably the most valuable cycle in the whole pipeline. This is going to give you the best information. We want an answer in under 5 minutes that gives us a high level of confidence that the software does what we think the software should do at that point. Or at least the software is what I thought it was when I wrote it. And so it's worth investing time, energy, effort, money on this stage This is probably that gives you the biggest feedback, the biggest bang for buck by getting really efficient feedback at this point of the process. So, if your commit stage is starting to slow, if you've got your tens of thousands of tests and large amounts of code, start thinking about ways in which to speed it up. And the first one is if your build, make sure that your builds are efficient. For some reason, our build scripts are one of several places that we tend to take our brains out when we get involved in those, and they tend to be fairly low quality. They tend to be poorly maintained, not very modular, not very well factored very often. So do the work, make them, treat them as a serious bit of software, measure the cost of different parts of your build system, and understand where you can effectively improve it. The other simple solution is buy some faster hardware. This is not a bad solution. I worked for a trading company once, and I went to my boss and said, I can reduce the cycle time for your automated tests by a factor of 10 if you let me buy this big box. And he gave me a budget and he allowed me to buy it. And it made a huge difference in terms of the quality of feedback that we were able to gain. Just throwing hardware at it, this is a good place to do that. We can parallelize the build. Modern build systems are phenomenal. Incremental build systems. I had some bad experiences early in my career with incremental build systems that weren't very reliable. They are wonderful these days. And you can do this at massive scale. If you look at the way that the builds in Facebook and Google and those sorts of places operate, they're building massive amounts of software in minutes. And that's largely because they're not building them, they're just reusing the stuff that they've already got. They're just evaluating the changes and patching the stuff that you've got really effectively. So parallelize the build. There was a wonderful talk earlier today about continuous delivery in the games industry. They've got a parallel build farm of 150 servers building their software and giving them really great feedback. That's the kind of thing that we're talking about. The other solution that you can think about is to decompose your system into smaller modules. And this is a good solution, but there are some dangers here. Each module has its own deployment pipeline, and you can evaluate the changes. This is what I spend quite a lot of time working as a consultant and going and talking to reasonably large enterprises about trying to adopt continuous delivery. And this is the solution that all of them jump on. This is what they assume is that they must do. This is what they assume is the only way in which they can achieve these short feedback cycles. But there are some dangers here. You have to think really carefully. Oops, sorry. Pressed once too often. There are some dangers here that you need to think about carefully. This is not as easy as it seems, because dependency management and worrying about the interaction of different parts of your systems is one of the genuinely hard things in software. We're all aware of how fragile our assumptions are of APIs. We can have an API that doesn't change. We change something in the implementation underneath it, and that might leak out and cause a problem in the things that use it. All of those sorts of problems. And so this is a genuinely hard problem. Microservices, when applied genuinely, you don't test the services together. They are independently deployable. You trust the protocol. That's part of the definition, really, of what a microservice is. If you're not doing that, if you're building your system in these little services and then you're testing them all together because you don't trust them together, that's not a microservice architecture, it's something else. So you need to think about these things. Microservices is no silver bullet. Remember, independently deployable units is the scope of a deployment pipeline. If you can't consider pushing the button and deploying this piece of software alone without testing it against something else, it's not an independent deployable unit, and you probably need to think about the scope of your deployment pipeline differently. So this is alluring. Everybody wants to do this because it sounds easy. Unfortunately, in the real world, it's not easy. The good news is that if you can't achieve that, it's a good strategy, don't get me wrong, it's a good strategy, but it takes careful API design, careful protocol design, loose couples, architectures, all of those kinds of things need to come to place for you to be able to do that modular strategy. The good news is that actually the other way of doing it, the monolith approach, is way more scalable than most of us think of. You can do this on vast scales, and modern build systems are really great at managing distributed farms, compute farms that you're able to throw big builds out to, your large C++ builds, those sorts of things. I had a great experience of trying to do a very large-scale C++ build, and we got the time down from 9 hours to 12 minutes, including running all the tests, by doing these sorts of things. One of the things for some of those technologies that's worth trying and that I have used is try running it from RAM disk. Actually, that's a little bit better than solid state disks. SSDs don't quite have the same I/O bandwidth, and so if you put it in RAM disk, you can actually get some quite fast feedback results for certain times of I/O bound builds. The real answer here is measure it. Is profile your build, understand the implications of what's going on, measure the performance of the different parts of the behavior, and optimize those. Again, I want to repeat, this is a good place to invest in this sort of engineering. This crucial feedback cycle in the commit stage is worthwhile expending time, effort, and money on. What if the tests are slow? If the tests are slow, look to the tests. It's no good looking in the wrong place. The problem here is not the donkey's, well, in one sense it's the donkey's problem, but it's not the donkey's fault. And so, look to the tests. Examine the tests. Think about the design of the tests. Think about how to improve those over time. Think about how to speed them up. Commit stage tests should be pure unit tests, and by that I mean they don't start the application, they don't write to disk, they don't write to the database, they don't use the network, and they fake dependencies. I'm not going to name it because that's too rude, but I run courses on test-driven development, and one of the things that I do is that I take examples of bad code from open source projects. And one of the examples that I show people is from a very, very well-known open source project. I would bet that a significant proportion of you people in the room use this open source project, which I'm not going to name because it's in our kind of space. One of the unit tests starts the application up, runs the whole application. It's got some nice little waits in there to delay, to wait for the application to come up. And then it tests to see if there's a URL, if it says localhost in the URL for starting the application up, it should reject the application starting up and it should stop. That's the unit test, okay? If you were to slightly redesign your code, so let's say for argument's sake you had a Jenkins URL, then when you start the system, instead of starting the whole system, you could just say, does the URL throw an exception when it's got localhost in the name? That would be about 4 or 5 orders of maybe more orders of magnitude more efficient in terms of speed and efficiency, in terms of speed and latency of trying to get the result. So we want our tests to be pure. We want them to be fast. We want them to give us high levels of confidence, but we want to think about them intelligently. We don't want to be naive about the way in which we test these things. We want to be really, really cautious about slow tests. There are times when slow tests in the commit stage are valuable because what we're looking for from the commit stage are 2 things. We want fast feedback, and we want a fairly high level of confidence, if all of those tests pass, that this change is going to be good. We are going to evaluate it further later in the pipeline, but we'd like, say, 80% confidence that if it passes all these tests, it's going to pass all the rest of the tests in the pipeline. That's kind of what we're looking for. So there are very few occasions where you might accept some slow, inefficient tests in. You want them as efficient as you can make them, but you might accept some slow tests in the commit stage because they're extremely valuable. But be really, really skeptical of slow tests in the commit stage. Always think about efficiency when writing tests. Always think, is there a cheaper way of getting this answer? What's the easiest way? And this has a wonderful knock-on effect because nearly always the way to get a good answer from your testing is to write better code. So if you do test first, test-driven development, you drive out more modular code. Because you design it in a way that makes it testable. And guess what? Testable code tends to be higher quality because it's good separation of concerns, more modular, loosely coupled, all of those good things. Use chicken counting. Don't have tests that do thousands of iterations. 0, 1, or many. If it's, if you're iterating over a loop over it 3 times, that's enough to satisfy the 0, 1, or many criteria. Use mocks and stubs to fake out dependencies. Remember what I said before, never talk to the database or the network or anything else. Fake those things out while you're testing in the scope. Testing these little abstract universes that you create. Periodically, get the whole team to have a test performance day. Sort your tests into the order, rank them in terms of how long they take to execute, and then get everybody focused on trying to speed them up. Is there a cleverer way in which we can learn this thing? Run tests in parallel. One of the nice, if you follow the INVEST principles, if you make your tests atomic and isolated from one another and not dependent on one another, you can run them in parallel, to the limits of the processor. And then if you're really smart, you can farm them out onto other servers as well. Effectively, you can kind of say, how long does it take me to get my test results? Well, it depends how much money I want to spend. I can turn the volume up, spend more money, and get the results faster. Ultimately, it's not quite linearly scalable, but you can get very close. As a last resort, if there are slow, problematic tests, but they are high value, then move them out of the commit stage. This is, as I keep saying, this is really valuable real estate. It's worth compromising coverage at this stage to some degree for fast feedback. We want a high level of confidence. We don't want to dismiss coverage. We want to test pretty much everything in our commit stage, but we want that to be fast. And if there's something that we can't test quickly, and we've run out of ingenuity, then think about moving out into a slower test just to get results. The analysis stage is really useful. Static analysis can give us really great feedback on the nature of our code. I'm a particular fan of things like automating coding standards. If I commit a change that doesn't fulfill my coding standards, it's rejected by the build. But also giving us other insights. Am I fulfilling my architectural principles in my software? Am I trying to inject something that allows me to talk to a database into my UI tier or something stupid like that? Whatever it is that I care about, I'm probably going to find a way of testing it in some way. And so I want to get that sort of feedback. You can get some really great tools. You can get in the Java space. There are things like there are lint style tools that give you those sorts of things, but static analysis tools that will do cyclomatic complexity measures. You can reject code, changes on too many parameters in your methods or too much code in a block, and all those sorts of good things. And all that stuff is good, but again, we want the results quickly. Remember, it's got to do this, and it's got to give us an answer in under 5 minutes. You might be able to run the analysis in parallel with your unit testing and maybe even the compilation, but you want an answer back in under 5 minutes. So it needs to pay for itself. It needs to be giving value. If the analysis doesn't catch bugs, then drop it. Think of the execution time, the CPU cycles that you're spending on evaluating your commit stage as a valuable resource, and manage them carefully. Make sure that you use them efficiently, and think about how you're applying those. If something never catches a bug, you've got to question whether it's being useful or not. As a last resort, move the analysis out of the commit stage. I think this is a very last resort, really, because actually you want the analysis, you want the feedback, you want to reject changes quickly and early on the basis of some of these criteria. But if you can't do it, if you want to run one of the big tools to do code analysis, they're usually too slow, so you are going to have to move them out. Try and find a cheaper way to get some of the benefits of the analysis in your commit stage and get the more heavyweight static analysis externally at some later stage in your pipeline. As a last resort, give up. Don't bother with the analysis. If the shortness of the feedback cycle is more important. It's more valuable. We want to test the release candidates and that they make it into production. Part of the definition of the commit stage in the continuous delivery book is that the commit stage, as kind of the closing act, will create the installers. It will create the deployable units that represent our release candidates. For some kinds of technology, those can be quite hard to create. I worked with a team that were building software on FPGAs, and we were doing continuous delivery with FPGAs, and actually you can't burn a new FPGA in 5 minutes. It just doesn't work. So you're not going to get the feedback, so we would do a whole load of stuff in simulation, and then we kind of pushed that part of the problem further down the pipeline. So the output of a successful commit stage is deployable software, and this is difficult to achieve for some kinds of technologies. So the answer here is just move it out of the commit stage. This is less of an issue than any of the other things, moving other tests or your static analysis, because actually this very rarely goes wrong. This is not the sort of stuff that really breaks your build very often. If you've run all of your tests and all of those work, you're probably going to be able to build the installers. It's unlikely that those are going to break at that stage. And then there's kind of the human continuous integration thing. So we want to run the test locally before committing, wait for the results of a commit build, don't go home, don't go to lunch, don't go to a meeting, and so on and so on. Fix or revert the failures within 10 minutes. If a teammate has gone home, if they've broken this rule, revert their change on their behalf. Send them a polite email saying, you broke the build. Please try not to do that in future, but I was your friend and I reverted on your behalf. If someone else notices that you broke the build before you notice that you broke the build, that's a build sin, and so you should pay a penalty. Various teams I've worked on, we had to wear a silly hat until the next person broke the build, and we also had a sin at LMAX, where Steve and I worked together. We used to have a sin jar, and you had to put £1 in the jar every time somebody else noticed that you broke the build before you noticed you did. And once the commit stage passes, move on to your next thing. Continuous delivery is about optimizing the process to keep the software in a releasable state. That means that pipeline failure is a top priority. So we want the fast feedback. We want to be able to understand the implications of our changes. And when we see a failure, we drop everything, stop the line, fix the problem before we move on. Mostly what I've just described is kind of classic continuous integration. We've got a version control system. We're going to trigger some evaluation in our commit stage and kind of generate some a release candidate out the back of that. That's human CI. Another optimization is gated CI. This is an optimization because it skips the need to run the tests, all of the tests once. So instead of running them twice, once on the local developer's workstation, then once again in the CI system, you can make that slightly more efficient by gating the process. So in this model, instead of committing to a version control system, we commit to the commit stage, we run the tests against it. If the tests pass, then the commit stage promotes the changes into our version control system. And that can work quite well. There are still some issues around the error reporting and so on, but that's another way of thinking about making things a bit more efficient. So, in summary, the performance of the commit stage really matters. Teams with a fast commit stage tend to keep the build green. There seems to me, this is a subjective impression, but it seems to me that there's a relationship between the length of time that you have feedback and the proportion of tests that you have that are always failing in your builds. If you have a feedback in under 5 minutes, your builds will pretty much always be green because it's really easy to fix them. If it takes 40 minutes, 5 or 10% of them are probably going to be a bit flaky, and you'll just accept that it's okay because they always fail. Next, slow acceptance tests. So here's our acceptance test stage. These are tests from the perspective of an external user of the system. These are tests that are trying to evaluate the software as a whole. We want to test our deployable unit, whatever that is, in lifelike circumstances, in production-like test environments, in realistic scenarios. Here's my pseudocode. We want to configure the environment prior to deploying the system, deploy the release candidate, smoke test or health check to make sure that the system's up and running, ready for work, and then run some acceptance tests. That's the kind of thing that we want to do. Ideally, we're looking for a cycle time in the order of about 5 minutes. Sorry, 45 minutes. What we're looking to achieve overall is we'd like the entire cycle to take under an hour. And again, this has one of these kind of slightly soft and fuzzy reasons, but it's about the feedback cycles again. So let's imagine that we're working in an organisation that does overnight builds. The build's too big and too complicated, and we get feedback once a day. My bet is that an organisation like that is running with somewhere like 10 to 15% of their tests permanently broken. Different 10 to 15% tend to be fairly random, but there's going to be a proportion. And that's because if I commit a change as a developer which causes a test to break, I'm not going to find out about that until the next day. My thinking's moved on. I'm thinking about something else, but I'm going to find out about it the next day. Now I've got to drop everything, go back to where I was the day before, understand what I'm doing, and try and figure out what's going wrong. Meanwhile, lots of other changes have happened, and it's all complicated and horrid. And I'm going to commit a change that day, and I'm not going to find out whether that worked until the day after. Does that sound hard? It does to me. Well, it is hard. If you can shorten the feedback cycle so you can commit your changes multiple times a day, you can learn that lesson within the day. You've got a better chance of being on top of the change and understanding it. Let's say that we had a build that was 2 hours long. If I'm a developer and I commit a change and I screw up, I've probably got 2 attempts at correcting the problem before the end of the day, and I'm into horror world that I've just described. If I can get that feedback in an hour or less, then I've now got 5 or 6 attempts to sort out a problem that I introduced, probably 3 or 4 on average across the day. And that gives me a much higher probability of keeping the test passing. My experience is just reducing that cycle time in this way will allow developers to stay on top of failing tests and start addressing the flaky tests and all those sorts of things that tend to crop up. So where are the things that can go slow? So it can be slow to configure the environment. I had a client last year who, as part of their deployable unit, they had 150 gigabytes of data that they carried around as part of their deployable unit. Actually, it was test data and it wasn't used. So that was ridiculous that they were moving all this data around to no good end, but it meant that they couldn't deploy their software in under a couple of hours for a bunch of other reasons as well, which really slows you down. You can't get feedback multiple times a day. So start thinking about that, taking that seriously. Start thinking about the different rates of change that occur in your application. Presumably, your source code is going to be changing at a much higher rate than the version of the language that you're using, or the version of the operating system, or the configuration of your database. Those things are going to change at different rates. So you might think about staggering those and managing them differently so you can optimize. So effectively you can have incremental deployments. You can think of those sorts of techniques to speed things up. One of the things that I've been doing with one client is pre-configuring environments. So effectively you have stamped out cookie cutter images for environments that you can then kind of start layering on top of, so that they've got pre-prepared things, and that's happening offline. So all of the time they have some systems that are preparing these canned environments for change, and then when a change comes in, it can be deployed. If you update some of the definition of those environments, you scrap the canned ones that you have and you start building some new ones. But think about the time and the way in which you can carve out the time. Think about layering the configuration and managing that appropriately so you can get to more efficient deployments. Think about the amount of data that you've got to ship around your network and how you can minimize that. How can you minimize the amount of stuff that you're figuring around? Your talk earlier on, I loved your talk, by the way, talking about continuous delivery in the games industry. You're talking about minimizing the patch sizes so that you haven't got to ship large volumes of bytes around, so you can update more frequently. Use the system efficiently. Consider versioning pre-baked image templates and using those. Consider the use of containers and Docker. One of the good things that Docker does is that it takes care, at some level, it takes care about some of these worries. When you deploy a container, it will take the image and it will look at the a version of the image that's already in a cache somewhere or something, and it will only update the layers in the image that it needs to. It doesn't update the whole thing. So you're not necessarily shipping hundreds of megabytes around every time. It's just going to pick the bits that have changed, the layers in the version control system that's built into Docker that have changed. Successful deployment ends with a working system. So for the efficiency, we need to consider the time to deploy. How long does it take us to get our system up and running? How long does it take us to migrate the data associated with that system? That might challenge you to do intelligent things around data migration. I have a client at the moment that works in the healthcare industry. They deal with massive volumes of data, medical data in different fields. And so when they have a big migration problem. So one of the things that we've been talking about is thinking about different, cleverer ways to do that. Build some behaviours into the application so you can effectively do lazy load data migrations at runtime, at the point at which you're going to read the docs. You say, oh, this is in an old version. I will translate it for you on the fly, and you won't notice. So you share out the time, not do this all at deployment time. Think about those sorts of techniques too. Think about the time to start the system, make it more efficient. Try and remove dependencies between different services because you don't want different parts of the system waiting for other things. Think about other architectures that you allow you to start the system up in parallel if it's distributed. And then there's the time to validate the system to make sure that it's up and running and healthy. Think about monitoring, building that in and integrating that into the system as part of the design of the system to give you good feedback. Keep the deployable artifacts lean. Take it seriously. Don't just kind of bundle everything in that you've ever seen that you might one day want in your application. Think about the stuff that you need and delete the stuff that you don't need. Try and keep the amount of data that you're shipping around as small as you can get away with. Packaging can make a big difference. The way in which you package things, the way in which you dependency manage things can have a big effect on your ability to start taking advantage of some of these tools. Think about the design of that. Think about the allocation of that. I've talked about some of the layering strategies that are used in containers. Dependency management systems do some similar kinds of things, and they can help you if you use them intelligently. Think about the network infrastructure and constraints at deployment time. Just how much data have you got to ship around? What are the theoretical limits? What does that mean about what's possible and what's not? And think about caching strategies and so on to work around it if it's going to get in the way. Minimize data sets wherever you can. Try and keep the scale of the system small. I'm not a big fan of dumps of production data into test environments. I want to synthesize my test environment. It gives me higher quality testing, and it means I don't have to ship as much data around. I can generate it on the fly rather than ship large volumes around. Consider better modularization, independently deployable services again, and it's cropping up again, but it's a strategy that's worth considering. I've mentioned this already, I got ahead of myself. Minimize startup dependency and ordering. If you've got a system that's, a service that starts up and it's got to wait for that other service to start up before it can finish its initialization, that's a bad thing. Think about that in the design of your system. So this isn't just a deployment type thing, it's an architecture thing. Think about building a system so that it can start up in parallel and then coordinate once everything's up and running to have a whole system that's running. Think about using asynchronous design approaches may help with those sorts of considerations. That's another one of my hobby horses. Invest in optimizing the code that's executed during startup. We had an odd play. I was involved in building one of the world's highest performance financial exchanges while I was writing the continuous delivery book, and we were really good at automated testing on that project. But one of the things that we did in our acceptance test environment was that we would run we would configure the system to isolate our tests. And so we optimised the bits of the code that were about things like account registration or setting up a new market in which to trade. And they worked in very, very short orders of time as a result. So you might think about optimising these things. Think about the startup time for your services, and think about, are there ways of taking work out of those times so you can get the system up and running more quickly and get to a point where you can start testing more quickly and more efficiently. All of these things have knock-on effects that make the system nicer to use and higher quality. And that's a good thing. That's one of the great things about continuous delivery. We do these things because we want the feedback, and then as a knock-on effect, what we get is that we get higher quality systems as an outcome. Think about better modularization. Think about how to divide it up and how to isolate some of the costs that you see in the system. One of the things I've been practicing continuous delivery for a very long time now, and so I've seen quite a lot of teams go through kind of the adoption phase. And there's a pattern to this. And one of the key patterns that I see, particularly in acceptance tests, are the whole system tests in a production-like environment, evaluating in life-like circumstances, remember? And so they're expensive tests to run. And so what you tend to see is that what everybody does when they start up is they buy a server to run their acceptance tests on. And then they start writing acceptance tests, and then they start motoring, and they're going along. They're using acceptance test-driven development as part of the cycle. They're really flying. They're building these multiple acceptance tests for every feature that they're building, every story that they're completing. And gradually, over time, they get enough acceptance tests where the results start to get slower and slower and slower because there are just lots of them. They've done all of the tricks of optimizing it and running it in parallel on one machine. It's time to buy another machine. So what everybody does the first time is that they just kind of manually scale up. And so they just buy another machine. And then they artificially divide the tests in half and run half on one server and half on another. And that happens, and then sometime later they hit the next stage, and they buy another 2 machines at that point. And then they manually divide it up. And this is the point at which they start to get pissed off because they're spending a lot of time manually trying to balance the test runs between the machines. And so then they start thinking about automating these things. So we want to parallelize the acceptance tests. Initially, it's fine to do it tactically. That's a decent strategy. It's simple, it's cheap, and it's effective. But over time, it will become a burden, at which point you're probably going to end up writing something that will start allocating tests dynamically to different services and managing a grid of services. I think this is a prime candidate for an open source project, and I haven't seen one that does it yet. I've built this about 3 times in different projects now, but it's a really good effort. So I hope somebody, maybe me one day, but I hope somebody's going to build something and put it out in the community. But treat acceptance test isolation seriously. It makes all of this really easy because we can run them in parallel. We can farm them out. We don't have to worry about them. Treat them as atomic. We don't have shared data sets. We don't have ordering in our tests. Here's a... sorry, no, not quite. If we've done all of that, if we've done the thing of keeping the tests isolated, it makes scaling up easy. So here's our acceptance test stage. We've got it becomes free. It looks for a release candidate in our artifact repository. It pulls it down, deploys it to a shared test environment, and then it spawns out a whole bunch of hosts to run against. That environment, and we can kind of scale up. We can kind of have loads and loads of hosts. We can have multiple ones of these if we want. We kind of manage all that on a soft basis, and so we can really scale up very, very significantly. Here's a nice animation of the dynamic allocation of some of those tests running in the LMAX environment. There's a couple of things going on here. So some tests you can run in this shared environment. Some you can't afford to do that. They need dedicated environments. So you can see this is dynamically allocating tests and hosts to various scenarios, and is managing a grid of computers in order to execute these tests and parallelize this. Again, ultimately, the rate at which you can get feedback is the speed of your slowest test, a function of the speed of your slowest test and how much money you've got to buy hardware to run tests on. Failing tests. So the efficiency of the feedback cycle is central to the ability to keep tests passing. I mentioned in passing the trading company that I worked on. We had a large C++ build. It took 9.5 hours doing overnight builds and overnight test run. And in the 3 years preceding my involvement on the project, they had on 3 occasions, three days in 3 years, they'd had all of the tests go green. Yay, they had cake on those days. We did some of the techniques that I talked about here. We rewrote the build scripts. We threw hardware at it. We ran it off RAM disk. We did everything that we could think of. We measured it. We did experiments. To cut a long story short, we reduced the cycle time from 9 hours to 12 minutes, plus acceptance tests. Basically, just anything that was slower than a couple of seconds, we called it an acceptance test in 30 minutes, and that made a huge difference. And so as a result of just that change, in the following 2-week period after releasing that build, there were 2 occasions where all of the tests were green, and in the 2 weeks after that, every single day there was a release candidate where all of the tests were green. So from then on, we were able to just pick the newest release candidate that passed all of the tests and deploy that into production. Just the feedback, just shortening the feedback cycle allowed the team to stay on top of the failures. So we want this to be efficient. We want a short feedback from here. We want under an hour from here. And that gives us the ability to stay on top of failing tests. Continuous delivery is about keeping the build in a releasable state. We want to treat our tests seriously. If we have one test failing, the build's blown. We can't release it. So we have to take this really seriously. Prioritize fixing failing tests. Focus on keeping those down. Reduce the cycle time, and that will help. And then you get into the intermittent tests. So intermittency is a serious pain, and certainly if you've got a system of any complexity, it's kind of going to be part of your life. It's going to be part. You're going to have to find ways of dealing with it and coping with it. We did all sorts of things on the Exchange project. We were good at automated testing. We lived with the intermittency for way too long, and we kind of categorized them and ignored them for a bit, and then found out that they were telling us something serious. Too many teams live with intermittent tests. It's not a good thing. I think it's one of those things. It's a false economy. Some CI systems give you the ability that if a test fails, it will allow you to say how many times you'd like to run the test again. I think this is insane. If it fails once and then it passes once, which one's telling you the truth? There's no way of telling. You can't tell which is the truth. So I want my test to be definitive. If it fails, the test that release candidate is not going out. And so I'm going to treat a test failure as something serious, even if it's intermittent. And there, I'm going to expend the energy to try and get to the bottom of it and fix the problem. So don't live with intermittent tests. Spend the time to fix the problems. It can be expensive. It can be time consuming. It can be a real pain in the neck, but it's worth it in the long run. Once we got to a certain level of capability in building our Exchange, every single time we dug into an intermittent test, it was one of two things. We'd either got something trivially wrong in our acceptance testing framework, and so it was easy to fix and easy to reuse, or it was indicating a real serious problem that we hadn't thought about in our system that would have caused a production outage, or production problem anyway, had we not found it. So treat intermittent tests as failing tests. Expend the energy to fix them and address them. As a last resort, you've got to question the value. If a test is intermittent, so do track your intermittent tests, but if a test is intermittent, what it's doing is half the time, at least, it's lying to you. And so you've got to question the value of keeping it around. It's giving you a bad signal, and you've got to decide what you're going to do about that. Common causes of intermittency in tests is race conditions, particularly in asynchronous system, poor test isolation, so think about those, poorly designed test cases, and sometimes it's something real, it's something serious. And so it's always worth digging in and trying to find out what's going on. Finally, pipeline changes. One of the things that kind of is mildly amusing is if you think about most of the build management systems that we kind of come to know and love or not, you know, the Team Cities of the world, Jenkins, those sorts of things. Traditionally, they've been really, really poor at being version controllable. I think some of them have got a little bit better in recent years, but we need to start thinking about this. If our pipeline is this strategic resource, it's our channel to production, it's this substrate that allows us to perform development, it's important to keep it up and running. And so we need to think about how to manage changes to our pipeline. Simply, we want to be able to version control those for a start, for sure, but we want to think about those. Interestingly, we can think about these kind of traditional sorts of things to address the problem. We can think of it as a strategic resource. We can think of service level agreements and clustering, a high level availability. Those sorts of things are probably a good idea. But the other part of this is that we've got quite a good strategy for dealing with complexity in software. It's called continuous delivery. It allows us to do testing and evaluation of things and version control things, and we can apply that to our pipelines. We implemented in one of the organisations I worked in, pipeline as a service, horrible term, but we had a team, and one of the things that we did was that we had a little test suite of tests which had a dummy project that would start up any changes to our pipeline on this dummy project, run through the dummy project and see if the pipeline worked. We had acceptance tests for our pipeline and a deployment pipeline for our pipeline, which screws with your head a bit, but it's worth thinking about. So pipeline is a complex system in its own right, and we need to consider it in those things. Think about versioning it and the tools. Consider writing test cases for some of the key pipeline behaviours and evaluating those behaviours, because it's important. If it goes wrong, you want to find it out quickly and efficiently so you can revert. Consider blue-green deployments for pipeline changes. Have two versions of the core infrastructure of your pipeline, or cloud infrastructure, and immutable servers or whatever it is. But think about those sorts of strategies to be able to use those sorts of techniques. Use an infrastructure as code approach to all pipeline hosts all of the time. You want those to be reproducible at the push of a button at any point. And do take it seriously. Think about the pipeline as the only route to production. All production changes go through the pipeline. If we do all of these things, what we get is that we get this amazingly powerful thing. We get this amazingly powerful facility to be able to carry out these experiments, to try out the ideas. The real value of continuous delivery, as several speakers that I've seen have spoken about today, is not about the technical practices. It's not about build automation. It's not even about automated testing, which is one of my things that I care about a lot. It's about being able to evaluate ideas in the hands of users. We have an idea. Does the users like it? Does it get there? It gives us a tool that allows us to evaluate that, understand it, and get feedback on that from our user community. That way we're able to learn, adapt, refine, and exceed expectations. That's it. Thank you very much indeed.